There you go. Okay. Maybe that'll work now. You still have to fiddle with the games and stuff, probably. That's what I thought. I was like,
I was thinking about the lights.
on it.
Yeah, I didn't see any lights.
You're sure you got audio now? Okay. You have Austin's audio too?
Test. Macaroni.
It's
on.
Oh, okay. She's got us. Oh yeah, it's got the lag, right?
Gotcha.
So because
Okay.
she's testing the YouTube stream.
Yeah.
Yeah. And we got more people coming in. This is perfect.
Yeah, we still people.
All right. Well, are you ready to go? Ash, you ready? All right. Thanks everyone for being here. There are still open seats both sides. You should still be able to see the screen no matter where you sit, so we should be okay there. So welcome to our strategic design talk at CCC 2019. We'll do a couple quick introductions. So I'll start. My name is Mike Corsetto. I'm the lead technical mentor for Team 1678 Citrus Circuits. This is going to be my 17th season in FRC. In my adult job, I'm an engineering manager at a company called SunPower. I manage a team that builds robots that clean solar panel fields in the middle of the desert. I started mentoring Citrus Circuits in 2008 when I went to UC Davis for college, and I've been mentoring the team since then. I put this on here as an important bullet point that I am definitely not the smartest guy in this room or most rooms I'm in. A lot of the stuff that you're going to hear in this talk is stuff that Austin and I have scavenged from other sources. Karthik has a lot of great stuff he posts, including his talk that he gives most years at the championship. If you haven't gotten a chance to see that in person, I highly encourage you to check that out or check out the recording on YouTube. And we've also stolen a lot of other ideas from other teams and sources throughout the years.
Hi, I'm Austin Haddox. I'm one of the lead strategy mentors on 1678. I'm a data analyst at an insurance company. So I deal with figuring out where money's coming from. And this is my 8th year in FRC, and this is my 2nd year mentoring 1678.
All right. You want to take us through an overview?
Sure. So we're going to kind of go through the season process. So we're going to go through what's happening right now, preseason, what's it for, and how do you go about it. We're going to talk about different drivetrain designs, mechanisms, different ways to move things with electrical, pneumatics, through the build season process, what is our season like, and what can you guys do to replicate that, and competition season, and some tips and tricks to go along with all of that.
Awesome. So we're going to start out by our first golden rule that's going to cover a lot of what we do on 1678 and what we highly encourage you to do with your team. Keep it simple, silly. KISS is the acronym. The bigger overarching thing is building within your team's capabilities. What we're going to go through this talk is how you can strategically increase your team's capabilities in the right ways and then leverage those increased capabilities during the season, and all the while not building outside of your team's capabilities, because when you do that, you risk taking on a lot of scope creep and other things that will result in not meeting your goals in season. So we're going to talk about how you can, fine-tune each of these areas of your team and increase where you can, turn those knobs a little bit more and more, and then utilize that during the season and the competition season. But the goal for all this is not going too into the deep end, trying to keep things simple and be effective in that. And this is going to involve building things more robustly. Another thing that, this is a side note, but for 1678, you'll notice, I think there's a lot of other teams that really get caught up in how their robot looks. And that's great, and that probably meets some of their goals. But for our goals on 1678, with regards to the robot, the only major goal we have is to win the world championship. So our robots tend to look pretty terrible when it comes to the rest of the competition. I have a funny little story in 2015. That was the year we won the world championship. there were a lot of teams that had heard about us but had never met us before, and they were very excited to see us at the championship. And they show up at the championship, and our robot is in like a pile of sawdust because we were making this cheesecake in our pit, and our pit was just a couple of totes and the table in the back. And there were a lot of people that thought they were in the wrong pit because they're like, this is 1678. What are we even seeing here, right? It's all about function over form. 1678 really prioritizes the ability to compete on the field above anything about how our robot looks or feels or anything like that. So let's talk about preseason prep, Austin.
So preseason is not a break. We focus on three main things. We focus on trainings through projects. We focus on trying new ideas and designs, new drivetrains, new ways for shooters, new elevator designs, ways that we can increase our productivity during build season so we don't need to try it then. And we also use that time to train our students on FRC history, look up different robots that were successful during different challenges, because FIRST tends to repeat different technical challenges. So certain designs follow 1 year to another.
That's great. Some ideas that you can do in the off season, things that could help prepare you for whatever's coming in 2020. Maybe do a couple of prototyping challenges where you build things like ball shooters or intakes. 1 year we had a game we played with, some of you will probably have like 10, 20. I know at 1678 we have a couple of hundred of those Fuel from the 2017 game, those big wiffle balls. We played a version of Hungry Hungry Hippos where we divided up our design team into 4 groups, and they each made their own intake. And the goal was to just pick up as many balls in a little Vex field as you could in like 30 seconds or something like that. And it gave a bunch of students on our team the opportunity to test out making intakes, things like that. Elevators are a common feature, especially the last couple of years. It's gotten pretty repetitive, actually. Almost all the robots this year have some sort of elevator. So elevators can be pretty common. Climbers, building the kitbot. So if you have an old kitbot, what you could do is you could just tear that kitbot down to each individual part and then build it back up as a way to practice for the kitbot that's coming in 2020. Learning how to build bumpers. We know for sure we're going to have bumpers this year. So getting good at building bumpers and technique with regards to that. A couple other things that aren't on this list that could be worthwhile is things like developing up your code base. So 1678 actually is going to be switching to Java for 2020, but we've already rewritten all of our 2019 robot code in Java. So the practice robot that we'll be playing with at Madtown is going to be running all on Java, but doing all the same things like vision and elevator functions and climbing that the competition robot could do this year, except it's going to be doing it all in Java. So that's one thing we're trying to mitigate the risk of switching over by rewriting all of the code from 2019 into Java, so then we can utilize that new code base in 2020.
So learn your game history. So every year it's stealing from a past year. So learning certain designs, strategies that can help you analyze this year's game, what to do. Some past histories. Climbing is a really common one, 2010, 2013, 2016, 17, but it was a little different, 18 and yeah.
Last year.
Yeah, well, it was different. But
a little
yeah.
different last year, yeah, that's true.
But so, inner tubes was another repeating. 2007 and 2011 both had intaking inner tubes and placing them onto little racks. Exercise balls of different sizes, 2008, 2014. And the lesson through all of this is the fact that look at your past game elements. If you see something that's similar, can you use a similar intake? Can you use a similar shooter? Way to interact with it? Because if you don't need to make something up, then you're saving yourself a lot of time.
Totally. All right, and that leads into golden rule number 2. Hope you're keeping track. Steal from the best, invent the rest. Doing that research that Austin just talked about is incredibly important to actually understanding what is the library of knowledge that is in the FRC world. Another thing that you can do to steal from the best, invent the rest, besides understanding what was built in the past, is there's all these great teams, Robot in 3 Days teams, that build robots within the first, it kind of flexes, but it's usually like the first week of the season. And they go through the whole process, and they'll actually walk you through their thought process. So they'll break down the game oftentimes, they'll show you how they were prototyping, and then they'll make these really fun videos where it's like a little robot reveal with their robot after 3 or 4 days, right? Those sorts of projects are super educational, and I can tell you for sure that 1678 is watching every single one of those teams. We're posting all of their videos into our shared Slack channel so that the whole 1678 team is tracking the progress of the community and the information that's being put out there. Because it may be that one small idea that a team shares that you can say, hey, I could take that and apply that to the direction that we're going on the team. And then if you want to know what it's like to build like simple and effective robots, there's a lot of great examples. Some of the teams on the screen here consistently build robots that aren't too complicated, but they elegantly complete the game task. So I'd encourage you to study some of those teams. Look at the way they build their robots. Look at how few degrees of freedom they have in order to get the functionality that they want. Those are all really good steps if you want to steal from the best and invent the rest. So, okay, drivetrain design. This is one of my favorite parts. Okay, look at these robots on the screen right here. I probably could have updated this slide with with 20. What am I missing? Oh, I'm missing 3 years of robots here.
Yeah.
But okay, so can anybody tell me what all these robots have in common? But the answer is not that they're all blue. Okay, yeah. They all have a West Coast drivetrain. So they all have a drivetrain. You can see it a little bit better in the picture in the top right, where they have a set of motors on the left side of their robot that drives the wheels on the left side of their robot, and they have a set of motors on the right side of the robot that drive the wheels on the right side of their robot. Can anyone think of a drivetrain that every rookie team gets that meets the same criteria? The KitBot. The KitBot does essentially the exact same thing that every 254 drivetrain has done for the last 20 years. Okay, the number of wheels changes slightly year to year, the configuration changes slightly year to year, but the basic concept stays the same. So the golden rule number 3 is use a proven drivetrain, and I'm gonna go on a limb and say for 99% of FRC teams, that is some form of tank-style drivetrain, namely the KitBot. So these are basic drivetrains that are usually 6 wheels, sometimes 4, sometimes 8, depending on what you're having to climb over. But the KitBot, and especially the KitBot with some modifications, Team 1114 publishes a KitBot on steroids video that may be a little outdated at this point, but it still teaches you some concepts on how to make your KitBot more robust. That drivetrain is such a gift for teams because it lets you spend the time your time is the most valuable aspect of your season. It lets you spend that time that you would have spent designing a fancy drivetrain on the rest of your robot that's actually going to win you matches. Because a KitBot with the best mechanisms in the world is going to beat the snot out of a custom swerve drive that has jack for scoring. Right? That's the basic principle of this, right? So we have a story related to this. There was a team that you might recognize in 2008 that spent a ton of time. 2008, you got these points for doing laps around the field, right? And you know, they said to themselves, okay, driving laps is going to be one of the most important parts. We're going to focus on that. But you know what? We're going to make our robot like a race car. We're going to have a custom steering. We're going to throw 4 motors onto one single wheel. It's going to be the best robot ever. Here's the robot. All right. And this is 1678. This is our 2008 robot rear cab. It was a custom steering in the front, 4 wheels in the back. The battery mounted 1.5 feet off the ground above the back center wheel. Every time this robot turned around the corner in 2008, it would roll over. All right. The team got so hyper-focused on this one aspect and thought they had to make a custom drivetrain in order to meet their team's goals that they ended up with this piece of inspiration over here, okay? Please do not be like 1678 in 2008, all right? Build the KitBot drivetrain. Spend your time building your mechanisms because your mechanisms are what's going to win you matches, and it's what's going to win you events. The KitBot drivetrain is just a means to an end. So I highly encourage the KitBot. Awesome.
So with mechanisms, it's really important to understand the geometry of them. So you want as little things moving as possible. So with degrees of freedom, with elevators, arms, wrists, if you want to, a turret, as if you can limit as much of this as possible, it's another thing that can't go wrong. You want low center of gravity because you don't want to tip over. You don't want to have your battery lifted up a few inches off the drivetrain when your robot is yay tall, because you're just gonna fall over. Especially when we're working with elevators, it's really important to have our center of gravity low, because when we're scoring on that third level of the rocket or scoring on the scale or whatever that year's game is, it's really important that we don't fall over, especially because defense is going to be hitting us at that point. We want our robots to be symmetrical, because when you finish one side, you know exactly how to finish the other. You don't need to worry with code about making sure that one thing is aligned one side is aligned a specific way. It just makes it easier for your drivers. It just makes it simple overall. Keep it simple, silly. We want to stay inside our frame perimeter, because every year, besides 2015, there's defense. So we want to make sure that our mechanisms aren't getting destroyed by the other team, because they're going to be trying to push you as hard as they can away from the scoring objective that year. And when we're outside of the frame perimeter, we need to make sure that things aren't going to break, because there are plenty of times where a team hits another team's intake and it shatters to pieces, and now they have no ability to pick up that game piece. They're out for minimum that match and maybe the rest of the competition, because they aren't able to repair it in time.
Okay, let's talk about a couple of options you have for moving things in mechanisms real quick. So motors, Sims, mini Sims, 775 Pros, Neos. There's a bunch of options for how to power things. There's more power now in FRC than there was 17 years ago when I started. You have all sorts of options for motors. Motors are great for allowing variable motion. They're great for intakes. They're great for shooters. They're obviously going to be used in your drivetrain. Where motors get a little trickier and utilizing motors gets a little stickier is when you want to use them for a degree of freedom that Austin was mentioning, some sort of controlled motion. So let's say an arm that's pivoting up and down, or an elevator that's going up and down, and you want to stop at certain set points. Motors are great if you want that variable control, but they come at a cost of oftentimes requiring some sort of feedback loop. So you need to have position sensing, and then you need to have some sort of control loop to accurately control that mechanism. There's a lot of tools now that weren't available even 4 years ago when I started giving this presentation. Things like the built-in PID controller on the Neo, or using a mag encoder with a Talon. There's a lot of stock software that can do a lot of these controls for you. And 1678 utilizes the heck out of Talons on this past robot. Every one of our major mechanisms, every one of our major degrees of freedom had a Talon and a mag encoder on it, because the Talon itself handles the control loop on board with stock code that CTRA gives you. So this movement with motors has gotten a lot easier in the last 4 or 5 years, but it's still something to keep in mind that every time you decide to have a controllable degree of freedom, it's going to require a motor and a sensor with the feedback loop, and you're going to have to tune that. And so the more you can minimize those, the better. The alternative you have to using motors is using pneumatics. Okay, and pneumatics are really great at going from A to B, all right, in and out, in and out. The other really nice thing about pneumatics is if it's a very small function that you need to do, like in 2019 and 2018, we had different ramps and wings that we use for partner lifts, all right? Those were held up by these little latches, and then those latches were just triggered by a little pneumatic, and all I had to do was go from closed to open, right? That's a perfect application for something like pneumatics. Or a lot of you maybe had intakes this year that would flop out. Intakes are often a really good candidate for using pneumatics, because oftentimes they need to stay inside your frame perimeter to start the match, and then they need to go out to a very specific position to pick up the ball or the game piece, whatever you're manipulating, right? So think about it and think, for this particular degree of freedom, do I have to use a motor, or can I get away with just using point-to-point pneumatics? The other side thing I will say is you need to be careful with pneumatics because it's possible to run out of air, okay? The little compressor you're able to use is not going to be able to take the heat if you throw one of those 2-foot long, 2-inch bore cylinders that I see some teams use every year, and you trigger it once and then you're out of air for the rest of the match, okay? So you have to pick the right application for pneumatics, and you want to be careful with how much air you're expecting to use in a given match. But if it's something where you're expecting to deploy and retract, between 3 to a dozen or a couple dozen times, and it's a small bore pneumatic, you're fine. I do not recommend ever using one of those massive pneumatics that you can buy on McMaster or get free from Bimba, where it takes 5 seconds for it to fully deploy, and then you're done for the rest of the match. Avoid those. If you're considering using one of those, figure out how you can use a motor instead for that degree of freedom, or just don't do it.
So for acquisition zone, it's really important because we have to pick up our game pieces. It's really important with the cargo this year because when we want as wide of a space as possible, because when we're grabbing the cargo, we don't want to be perfectly aligned. We don't want to have to perfectly run over this game piece so that we can start working with it. We want to touch it. We want to own it. We want it to be as easy as possible for our drivers and manipulators. And so with that, we want to stress prototyping with our different designs. We want to make sure that we have the best one possible, because this year we had, I want to say, 4 different hatch mechanism prototypes just to see what was the best way to intake it, what was the best way to spit it out. And both of those are different elements that are really important when working with the game piece.
Yeah, I think the acquisitions, just to go on that, this year, I think a lot of teams realized how important acquisition zone was just with taking hatch panels from the wall. If your design was such that it had to be perfectly lined up and your robot had to be perfectly square to get that hatch panel from the human player station, I mean, you could see teams sitting by the human player station for 30 plus seconds just trying to hook one hatch panel. The teams that really knew what they were doing, I mean, a lot of them probably had some sort of vision, but some didn't. The way that they did it was they either had like a little spear on the front, so even if they were off by 3 inches in either direction, it would center them into the hatch panel. Some teams probably here too have the double wheels. And the cool thing about the double wheels that would suck the panel in is if you were off by a little bit, the double wheel would literally roll on the hatch panel and center the intake as you were coming in. And that's an element of increasing your acquisition zone. And then the last thing I'll say about the hatch panels, just hopefully it triggers with you, acquisition zone isn't just about lining up like this, it's about your angle as well. And so a lot of teams this year figured out pretty early on that if they were going to be able to pick up hatch panels effectively from the human player station, they also had to have some angular compliance in their intake, so that if they happen to not come in totally straight and they would come in at an angle, their mechanism itself could comply with that misalignment and be able to still get the hatch panel. Everyone see how this acquisition zone can really make or break a driver's ability to intake a game element. So important to keep in mind, and like Austin said, important to prototype thoroughly. I'll go through Golden Rule 4.
Okay.
Is this the 4th one really, or have we only done 3?
No, I think this is the 4th.
This is the 4th one. I always lose track of these. So rolly grabbers. All right, so this is an important one to me. I want to highlight the same robots we talked about earlier, and I want somebody to list another thing that's similar between all of these, besides that they're blue, and besides that they all have the same style of drivetrain. Anyone else? Oh my gosh. All right, that's the third obvious thing. All right, what else? Yeah. They all have rolly grabbers. Look at this. It's hard to tell on this one, but like they used a rolly grabber to intake Frisbees in 2013. Obviously in 2016, they're using it. Even in 2014, they have these big rolly grabbers for the big aerobics balls. 2011, they're using rolly grabbers to pick up the tubes. If put in the right orientation and the right geometry, things that roll can pick up almost anything. Okay, maybe you need to have the rollers on the sides, or maybe you need to have them top and bottom, or just one on the top. It depends, and that's going to rely on prototyping. But rolly grabbers can do a lot. And the cool thing about the application with rolly grabbers is there's a couple different ways you can increase your acquisition zone just by putting rollers in the right orientations or using the right sets of wheels. So this example of 111, you can see how they have these rollers on the front that are bringing the ball that they're intaking in, but they also have rollers that are moving side to side so that if a ball comes in over here, it moves sideways and then centers on the middle belt and goes in. So they're taking this very wide acquisition zone and using rolly grabbers to center the ball and go through one slot in the middle of their bumper. You can imagine how much harder it would be to grab the ball if this whole intake was gone and they just had a roller at this slot and they had to line up the bumpers perfectly to the ball in order to pick it up, right? So this is the reason why teams use rolly grabbers and also have wide acquisition zones. So your robot looks a little bit more like a vacuum than it does a robot at times, and you're able to suck those game pieces up. Oh, these are more rolly grabbers. I forgot. Oh yeah. Actually, the funny thing is, of all these 254 robots we've gone through, I like giving 254 a hard time with this. This is the only robot to not have a rolly grabber, and it also happens to be the only 254 robot to not win SVR. All right. They've won every other year besides 2007 where they didn't use a rolly grabber. So use a rolly grabber, okay?
So we talked about with our rolly grabbers and our acquisition zone, it's really important to line up. With our intakes this year for the hatch mechanisms, we talked about rotational and linear alignment, but it's really important. And how do we guarantee that every time we go to that piece, we're going to pick it up or we're going to score it properly? And that can be done in a couple different ways. That can be done with using the limelights and code with some sensors to help align us by just pressing a button. Or we can have physical static objects that are either going to align us as we just drive forward by having those wedges, or maybe it self-aligns off of the robot to grab that piece, like a lot of the intakes this year.
Yeah, I'll add two things. One example was 1662. Any 1662 kids in here? No? Okay, I know they just got off the wait list a couple days ago. 1662 in 2013, it was the year of the Frisbees, and there were these goals you had to shoot in, and then there were these big pyramids that teams used to climb, and you got bonus points for climbing up. 1662 that year had these hooks that came up and would lock into the first rung of the pyramid, and the pyramid was always in the exact same distance away from the goal. So all 1662 did, they had no vision, no sensors or anything like that. They just ran full speed into the pyramid. They'd jam up against the bars on the pyramid, and if they were squared on the pyramid, they were always the exact same distance from the goal, and then they just shoot their Frisbees out, and most of them would go in. And they were able to they didn't have to wait in Finnick and hope that the vision was working and everything was calibrated right. They just ran straight in. It's like running into a wall and then just hitting the go button and scoring points, right? So if you have things like that you can physically line up on, it can oftentimes save you effort with code and complications that you don't have to go through. Oh, here's a picture of that robot. So you can see, here's the bars, and they had these hooks that would fold in and out using pneumatics because it was very simple. And they'd run those hooks straight into the bar and then just shoot a bunch of shots.
Another thing that's really important, every year there's often something that you can orient yourself on the field. You can run yourself into the rocket, and by just driving straight, you'll align yourself. But you do need to worry about linear alignment with that. But that's often a really simple way to forcefully align yourself to the field.
Yeah, good point. Okay, let's talk about electrical really quick. The big thing with electrical is you don't notice it when everything's working well, and then you really notice it when things aren't working. So there's a ton of things that can go wrong with electrical. Here's a picture of 1678's 2013 electrical work. This is our first year we went to Einstein, and somewhere in this rat's nest is an air compressor that's not mounted to anything. And we didn't realize that there was an air compressor that wasn't mounted to anything. And in the second semifinal match on Einstein, that air compressor decided to move halfway across the robot and hit the radio. And then the radio came unplugged, and we sat dead for 30 seconds, and we lost the match by a few points. So that was an example of what not to do, okay? What I highly encourage you to do is right now, you know you're going to have motors, sensors. You know you're going to have a RoboRio and a radio. Get familiar with those components. If you have students that are responsible for the electronics on your team, make sure that those students all understand what your best practices are, how you crimp batteries, how you crimp, Anderson connectors or power poles or anything like that. Make sure that they understand all of the basics of electronics work, how to route wires, because you're going to have to do a lot of that when you build your 2020 robot. You know that right now. And if your students on the team that are responsible for those tasks don't understand proper techniques, you're opening yourself up to risks when it comes to the season. So if there's things that you don't understand the proper techniques for right now, take the opportunity in the next couple months to figure out what those good techniques are and then incorporate them into your workflow so that when those students responsible for the wiring of your robot do that wiring in 2020, you know they're as best prepared as possible to complete those tasks.
So to add on that, it's really important to map out your electronics before you actually put them in, because then you lead to stuff like that picture right there, because, oh, this motor needs to get wired in, or we need to add this. It's really important to know how many motors you're using and where everything is, because you need to make sure that the wires are avoiding sharp edges so they don't strip, they don't short the robot. There have been plenty of times this year that happened to us, and it's an easy thing to keep your eye out for and make sure that it doesn't happen.
Okay, so I talked a little earlier about how a lot of this talk is just like we just talked about with electrical. It's all about getting yourself a little bit more prepared, and every time you make those little adjustments, you're preparing yourself a little bit more for the 2020 season. And what I was talking about earlier too about how we switched over to Java this year, but we didn't just say we were going to switch over to Java in 2020. We said if we're going to switch to Java in 2020, we have to know everything we need to know about Java before we go into the season, which is why we totally rewrote our 2019 robot software in Java. So there's a couple of key things that you can do with your software team in order to have kind of like a toolkit of familiarity with some common mechanisms and control systems that you may need to use in 2020. So one thing that you absolutely have to do is know how to drive somewhere accurately. I know we had Sandstorm this year, which helped a lot of teams drive in what was formerly the autonomous period, now the Sandstorm period. However, you still, if you really wanted to go fast, you still had to know how to drive accurately, not just for the Sandstorm period, but if you were using some sort of vision code, like a Limelight or something like that, you had to be able to drive in a controlled method using the Limelight. So understanding precision driving in general is an important tool to have in your toolkit, regardless of what year you're going into. So make sure that's something that's on your team's priority list. The great thing about this particular thing to put in your toolkit is if you're here competing, I guarantee you have a robot that drives. So you already have the hardware you need for the most part. All right. You just need to get more familiar with it and make sure that you can run autonomous routes. Maybe you had trouble with that this year. This is a great time to build up that toolkit because you have a couple more months before we go to the 2020 season. Vision alignment has become more and more of a thing. The Limelight is super great at doing this. So if you can shell out for a Limelight and get familiar with it, I highly recommend it. Well worth the time. And then I talked about using Talons and Magencoders. We also have the Neos now with the Spark Maxes. Get familiar with one of those platforms when it comes to things like shooters and linear elevators and rotating arms. All right. And building a shooter doesn't mean you have to build an entire shooting robot. You could honestly just connect the Neo to a shaft that has a couple wheels on it and mount the whole thing, and then you can learn how to tune a shooter wheel that way, all right? These may seem like trivial things, but like I was saying earlier, you're just twisting these little knobs and you're getting a little bit more familiar in strategic areas on your team so that you have those capabilities when you get to 2020. All right, we got to pick up pace a little bit.
So it's really important to have an accelerated schedule, and it's really important to keep yourself to it because driver practice makes perfect. And according to Karthik, driver practice makes bad robots win, and no driver practice makes good robots lose. I love that quote.
Yep.
But when you're making your schedule, it's important to aim for the stars and aim for the moon, land for the stars. So Mike can talk a little bit about. Yeah. So
I'll talk about it.
Yeah,
Basically, It's like if you're in this room, you're probably going to assume you have more time than you do. All right. And Parkinson's law indicates that that work fills the time available, okay? So what you need to do is you need to set a very accelerated schedule, give yourself a really tight deadline, all right? And even if you miss that deadline by a bit, you're still going to be way better off than if your deadline is our first regional in 2020, and that work is going to fill it. And often the most productive stuff is going to happen in the couple of days and long nights before your regional, okay? You want to have those really long, stressful nights 3 weeks before your first event, so you can spend 3 weeks doing driver practice like Austin mentioned. And I will say this is not just a student thing. Adults have the same exact mental lapses when it comes to scheduling, okay? Everybody assumes they have more time than they really do. You need to set yourself a very aggressive schedule so that you can finish early and do the things that's actually going to win you events like driver practice. Let's go through the schedule really quick. So days 1 through 3 is, this is 1678 schedule. So I'm just going to highlight that right now. Every team is going to have a slightly different schedule, but I want to throw this out there because I think it's a good foil for every team to think about when they evaluate what their own schedule they're holding themselves to is. So days 1 through 3 is our brainstorming time. And we're going to break through that right now, actually, because it's probably the most critical 3 days of our season.
So first thing, when first releases the game, it's really important to read the rules in its entirety. There's very small nuances every year that can very much change your strategy as to what you're going to build and how you're going to do it. First, before you talk about designs, it's really important to establish what you're going to do before you say how you're going to do it. So we're going to talk about that. And yeah.
So here's what so we talked about the rules, and on 1678 we have a rules test. So students can't actually go to the second part of kickoff without passing the rules test first. So everyone on our team does rules. We don't have like one rules expert. I highly discourage that. Not reading the rules is like trying to play soccer without understanding that you can't use your hands. Okay, you need to know the rules before you can play the game effectively. But the what's, this is what we're talking about right now. What are the ways to score? All right, and the ultimate goal from the what's is what will our robot do? So you need to understand, like Austin was saying, what's the strategy? What are each of the tasks worth? So we actually will list off all the possible ways to score. We'll also list off all the possible ways to like prevent other people from scoring. Then you want to try to evaluate as best you can, have a discussion around what's the difficulty of these tasks. How tough do we think it is to score a cargo in the cargo ship versus scoring a cargo in the top level of the rocket, right? What's the variation in the difficulty there? What's a little bit more reasonable than the other? Okay, and then Austin, you want to talk about design points for a second?
Yeah, so Karthik in his presentation has always talked about design points. So every team basically has a set amount of points that they can spend on different complexities of designs. So you can do one hard thing and one easy thing. An easy thing might be picking up a ball. A hard thing might be lifting it up with an elevator. That can lead to a lot of different things and can, if you focus on that and focus in your team's abilities, it helps you not make things overcomplicated. Because remember, KISS, keep it simple, silly. It's really important that you don't overcomplicate things. And every time you decide to not do something, you guys should be cheering because it's something that's going to be helping you save time, help you give that time to specializing in those specific fields that you do decide to go with.
Okay, we talked about, so we've decided what we're going to do. And on 1678, I think we have a picture of it down a little bit later, but we actually have on the list everything that we've committed our team to do. So all the functionality that we've committed to in 2019 or in 2020. So this year, it would have looked like we committed to picking balls up off the ground and getting hatch panels from the human player station and lifting ourselves and 2 other partners onto level 3. That was something we committed to on day 2. So we have this whole list. And once the team has established our list of required functionality, which we call the what's, then we move on to the hows, which is how is your robot going to carry out those functions that you have now committed to. And this is great because then when somebody suggests an idea that doesn't fall in line with the things that we've committed to, we can buzz them and say, hey, that's not allowed because that's not what we've decided to do. We've already decided to go in this direction. Okay, the whole team agrees to it. Boom, we move on to how we're going to do things. So this is where 1678 students will all share their ideas for how they think a task can be accomplished. This often looks like sketches or hand drawings. Every once in a while, someone will put up like a little sketch CAD of some mechanism idea or something like that. But most of the time, it's just to-scale hand drawings. And they're sharing designs that hopefully they have some experience with. So maybe they're like, a good example is in 2017 with the gears that year, all right? One of our students said, you know what, the gear looks a lot like the Frisbee did in 2013. If we just use the Frisbee intake, could we also pick up a gear with it? Turns out, yeah, we just put a battery to our motor on our 2013 intake and it scooped a 2017 gear right up. So we used ideas that we were familiar with and shared those with each other through this how process. How are we gonna do these things? Discussing passive things versus active things, and how do you process the game element through the robot. So you're trying to sketch up not just what an intake could look like, but hopefully you're thinking through how do I take the game element and then pass it through my robot, and then how do I ultimately score it, okay? Austin's gonna talk about that process a little bit more.
So with game object processing, it's really important to understand how the robot interacts with the game piece in its entirety, because if you don't understand how it's going to get to the shooter, then it's not going to shoot the ball. For example, when I was a student on 2085 in 2016, the intake and shooter designs were completely separate. And so when we realized, when it was time to put them together on the robot, they didn't fit together. And so the shooter came up through the intake and couldn't pick up the ball at all. So we had to completely redesign, which then cost a lot of time and functionality on our robot. Focusing on things that you have experience with makes a bunch of sense, because it saves you time, because you don't need to figure out how it's going to interact with a lot of things. A lot of people use flywheel shooters because you just have a simple ramp or track that brings the ball up to the flywheel. It's something that you don't really need to practice, but it's something that everyone can have experience with and you can prototype. So understanding all of the picking up, processing it to your shooter, releasing it, and aiming it is really important.
All right. So we're day 3. We've discussed what we're going to do, and we finalized a list. This is our example from 2016 of all the things the robot would be capable of doing that year. One of the things that was the biggest stretch for us was we committed to doing a 2-ball autonomous via the low bar. If you're familiar with that year, you know that was a pretty challenging task. Only a couple teams were ultimately able to do it, and even then, we were not 100% at doing it, but it was our stretch goal, right? And that's what we were committing ourselves to from day 3. Also on day 3, once we've committed to our strategy, we also commit to our drivetrain design by day 3. Like I said before, our drivetrains every year are very, very similar. And if they're not similar to something we've used in the past year, it's probably because we built it in the fall, okay? So we have a drivetrain design essentially out the door by the end of day 3. And I'm gonna highlight why that's really important for the rest of our schedule in a little bit. But day 4, we start prototyping mechanisms based on those hows we talked about earlier. So we have 100 students on the team. They're all sharing ideas to the broad group. We're writing them all down. And then we say, hey, you know what? These X number of ideas show a lot of promise. We think we can go in that direction. Okay, we'll split the team up into prototyping groups, and they'll each prototype those various mechanism ideas. Okay, so maybe there's like 3. This year we had 3 or 4 different styles of hatch panel intakes. We had a prototyping team on each one of those different styles, trying those ideas out, and they do that for like a week and a half. We're stealing ideas from Robot in 3 days. We're pulling in a lot of information, trying to gather it all together and come up with the best possible mechanism possible. We are also doing things in the design like the electrical layout on the drivetrain, the belly pan, so to speak. We're fabricating and assembling the drivetrain. So this is why we commit to our drivetrain day 3. It's so that our manufacturing students can start making parts. We can buy all the drivetrain components, like all the things that you would have to do after you finalize the drivetrain in like week 2, week 3, we're doing on day 3. And what that leaves us all the time to actually fabricate our mechanisms once our mechanism designs are done, which again starts happening after we've been prototyping. So you can either I think if you're going to be effective in 2020, you can either commit to designing your drivetrain by day 3, or you should be building the kitbot because then there's no design time needed, and you can just build the thing that comes in the box. But I don't think most teams should be spending like 3 weeks designing their drivetrain, because they're also having to spend 3 or 4 weeks designing the rest of their mechanisms, and everything's going to need to be made and assembled at the exact same time. But what we're able to do is we're able to finish our drivetrain by day 14. That means fully assembled, on the table, ready to get the belly pan wired up. All right, all the gearboxes are assembled, all the wheels are on, bearing blocks are in there, everything's done for the drivetrain. They can wire it up, and then by the end of day 16, all 3 of our robots are wired up and ready to start driving and running autonomous routines. Okay, this is all by day 6. I mean, we're like just over 2 weeks into the season. Okay, and we already have the most critical component of our robot finished, done, and we can focus on the things that are actually going to matter, which is the mechanisms up above. So you can be in the same boat really easily if you build the Kitbot. And I highly encourage teams to do that, because that means that all of your efforts can go into these day 8 through 21, which is building mechanisms, designing mechanisms, programming them. These are all the things that are really tough to do, because every year is a brand new game, brand new challenges, okay? But driving is the same every year. You just got to drive places. Sometimes there's little ramps, there's little bumps, but it's nothing super crazy. The important part is building mechanisms and programming mechanisms. And if some of your best people are stuck day 14 through day 21 designing a fancy drivetrain that's not going to do anything for you competitively, you're wasting a lot of resources that could be put towards things that are actually going to matter. So we're building and programming mechanisms day 8 through 21, and then the 4th week of build season, so we're starting days 23 through 28, is meant for our main mechanism integration, wiring, testing the code that the software students have written based off of what they're expecting the design to look like from the design students. So it's a bunch of integration. Austin, you want to talk about Golden Rule 5?
Yeah, so once your robot's finished, it's really important to test the heck out of it. We break our robot, and then we instantly go into fix-it mode. What can we do to make it better? We run it to the ground until our hatch mechanism broke so many times, and we had to redesign it over and over again. Our cargo intake, we realized that there were some issues with it. So then we realized, how can we fix that? We realized that using the 3D printed mechanism wheels made that a little bit easier. Mm-hmm. So we wouldn't have instantly came to that. So if you spend all of your time testing, breaking it, how do I fix it? Let's test it again, break it, fix it. You know, that's how you build a successful robot. All the teams on Einstein did not build that robot initially. They spent weeks and weeks of breaking that robot, replacing things, iterative design, and brought them to the place where they are able to be effective and efficient on the field.
That's great. All right, competition season. So this is the first year that this slide has changed in a long time. We used to have to bag our robot at the end of 6 weeks. That requirement is no longer there, which is exciting, but it's also a dangerous trap for you as a team. Okay, the illusion that you have more time should not be bought. Okay, that you need to have just as tight, if not a slightly tighter schedule than you have had in the past. Because what this now means is every team is going to be able to be doing this exact process of failing faster, testing, breaking, and fixing, not just until day 45, which is what it used to be with the stop build day. They're going to be doing that all the way up until your week 6 regional that you're competing in, right? And that means the robots that are on the field at the event are going to be better than they ever have been before. The entire field is going to be more competitive in 2020 than it has ever been in the history of FRC, and your team needs to be ready for that. And the only way your team is going to be ready for that is if you finish building your robot even sooner than you have in the past, okay? Because you will not be at that competitive level if your robot is coming together for the first time 2 days before your regional, okay? You have to build your robot super early and get tons of days, weeks of testing and driver practice and failing in the smallest ways and fixing those things, okay? Failing faster just became a lot more important because everybody just got a lot more time to fail. And if you're not using that time effectively to fail as many times as possible, you're going to be behind the rest of the competition, because your robot's going to, if you don't fail in your shop, your robot's going to be breaking in ways at the competition that other people broke in their practice field, all right, and they fixed those things and they got out to the competition without that failure mode present. But if you don't identify that failure mode in your own shop, guarantee you that failure mode is going to pop up in the competition. So you have to build your robot even earlier than you have in past years. Be more aggressive, because you have to understand that every other team in 2020 is going to be better than they were in 2019. All right, that's just a fact of the matter. The more access teams have to their robots, the better they get. Every robot's going to be better, and you need to try to stay ahead of the curve. So you've got to finish your robot faster.
With that, we need to stress the importance of after the quote-unquote build season ends, it's more and more important to spend that time as not a break, but it's still working as with that same schedule, because again, those teams are going to have that extra time to break, and they're not going to have a robot in a bag, so the robot's going to be more accessible than ever. Working on your robot's going to be easier than ever, and if you don't do it, you're going to be left behind by the 40 robots in the field.
Yeah. Another thing that you can do, which is a lot of fun, before you attend your first event, is watching other competitions. We talked about the steal from the best, invent the rest. Now is like the golden age of watching FRC around the world. I mean, FIRST actually includes standard broadcasting equipment to all their regionals. Most of the districts do a great job. I'm sure most of you have been to bluealliance.com/gameday, where you can watch as many broadcasts. You can put up like 9 of them on the same screen at the same time. It's just obscene. When I was in high school, like we could download like one little like QuickTime streaming file, and then we could like open up one webcast, and it was like, like 360p or something like that. There were like 5 pixels on the screen. You had to figure out what was going on. Now it's all HD. I mean, it's like it's the golden age of watching FRC around the world, and use that to your advantage. Study other teams. The best thing you can do, like we do these webcasting watching parties where we'll make pancakes early in the morning and throw webcasts on at 6 a.m. and just start watching matches and learning about the game. But a really cool thing that you can do is try to find those teams that maybe built robots similar to yours. Okay, maybe you built a robot this year that was a little bit like the Everybot, the Robo Not Everybot, where you could score cargo on the cargo ship and score level 1 hatches. If you build a robot that has a certain amount of capabilities, try to find the other robots at the events you're watching that have similar capabilities and see how they play. What are they doing in Sandstorm or Auto? Like, what are they doing for the end game? How are they playing the match? If they're playing defense and you're expecting to play defense in one of your upcoming events, how are they playing defense? What are their techniques? Rather than just watching the event as a whole, which is a lot of fun, try to focus on those things that you can actually glean some knowledge from.
Okay. So in summary, with the golden rules 1 and 2, we need to keep it simple. And what was number 2?
I forget 2. Oh, steal from the best and invent the rest.
Yeah,
there we go.
Yeah, no, that was 3.
Oh.
Research, I don't know.
Yeah, I don't remember. Keep going.
Anyway, well, with preseason prep, it's really important to prepare yourself for your next season. And with drivetrain design, it's really important to keep things consistent from year to year, so then you can practice, make it a little bit better for the next year. So you don't need to worry about it every year about what are we going to do to fit that year's challenge. With electrical and pneumatics, we need to keep it simple, keep it tight. We don't want things to get out of hand, because they can very quickly. And with build season, we need to make sure that we're strict with ourselves and hold each other accountable, because if no one does, you're not going to have enough time to practice and your robot's not going to get finished. And with competition season, it's really important to watch other robots, and really important to see how you can improve or implement other designs to make yourself more effective.
All right, some resources. Chief Delphi is great. Check out the Compass Alliance. It's an effort that 1678 contributes towards, where we have a bunch of resources published there as well, including a bunch of, we call them pathways, which are like 101s for different topics, including all the topics we've talked about today. All right, well, thank you, everybody. We're going to go through questions now. As we're doing questions, we have this like QR code, which I think you can scan with your phone. It's just a little survey that helps give us feedback on how these workshops have been for your team. So if you wouldn't mind right now, as you guys have questions, we're happy to take questions. Pull out your phones and scan the code and go to the little form there and just give us a little bit of feedback if you wouldn't mind. But right now, while you're doing that, we're happy to take some questions, and we'll probably repeat the questions so the live stream can hear it as well for the next, I think we started at 12:22. So I'm going to give us 7-8 minutes of questions. So any questions, guys? feel free. Would love to hear what you guys have. This slide or the one before it? Chief Delphi? Yeah, okay. Yep, okay. All right. Yeah, questions over here. Yeah. Why did we switch to Java? So I'm not a software guy. I'd have to talk to my software kids about why exactly. I know 254 uses Java, so I think that was probably a motivating factor. We were using C++. I think it was just a little bit too much of a learning curve for some students on the team. So I think Java is simplifying things a little bit for us. Also, our AP Computer Science courses at the school use Java, so there's a little bit more integration into more of the work that we do on the team.
Another reason for that is, like Mike said, a lot of teams, successful teams, use Java, so we can steal from the best, invent the rest. They make public their white paper and their code bases, so we can use that every off season. Yeah.
Yeah.
Yes, we do have a dedicated CAD team.
All right, well, we're good. We're good.
CAD's, oh, we're done?
Yeah, if you guys have questions, we can just talk later. That way we can just talk to you. Yeah, what's your question?